Hey everybody, Jonathan here. In this video, I will be giving you my take on section 7.3, which is all about trigonometric substitution. Trigonometric substitution is a pretty exciting integration technique, and you use it when the integrand, the stuff inside the integral symbol, has quadratic radicals. So a quadratic radical is something of a form the square root of plus or minus x squared plus or minus a squared. More specifically, the possible quadratic radicals are of the form the square root of a squared minus x squared, or the square root of a squared plus x squared, or the square root of x squared minus a squared. When you get such an expression, one way to solve the problem is to do what we call a trigonometric substitution. It's actually a form of reverse substitution, and the book goes over it and derives all this stuff, so I've just included the table here without deriving anything. However, my table has a little bit extra information in the book. So when the square root of a squared minus x squared shows up, you let x equal a sine theta. In which case, when you take the derivative, dx d theta will be a cosine theta, so dx is a cosine theta d theta. And furthermore, if you use the Pythagorean identities, you can simplify the square root of a squared minus x squared to be a cosine theta. When you've got the square root of a squared plus x squared showing up, you let x be a tangent theta, then dx is a secant squared theta d theta, and the square root of a squared plus x squared equals a secant theta, again thanks to various trigonometric identities. And finally, if the square root of x squared minus a squared shows up, you let x equal a secant theta, and then dx is a secant theta tangent theta d theta, and then the square root of x squared minus a squared becomes a tangent theta. Now these problems take a while, but they will all be done with the following steps. First, you choose the correct substitution, which is one of these three, however you have to say what a is. Then you're going to replace the quadratic radical and any other x's and the dx, which all are inside the integrand, and you can do it with all the information inside this table. At this point, you now have an integral in terms of theta, and you have to integrate with respect to theta. This can be really hard. You're always going to get one of those trigonometric integrals that we covered in the last section. However, they'll often be in a strange form with stuff in the bottom of a fraction where you're not used to it. So you're going to have to really work at some of these. After you've integrated, you then need to replace thetas with expression containing x's. A theta by itself can be replaced using inverse trigonometric functions like arcsine or arctangent. However, for the other trigonometric functions, you can always make a right triangle involving your angle. So for example, if x equals a sine theta, so sine theta equals x over a, you might remember that sine is by definition, well, one definition is that it's the opposite over the hypotenuse. So I make a right triangle with the opposite having side x, the hypotenuse having side a, and then the square root of a squared minus x squared is the adjacent side. And from this triangle, you figure out all of the other trig functions. For example, from this triangle, I can see right away that tangent of a is going to be x over the square root of a squared minus x squared. I'm sorry, tangent of theta is going to be x over the square root of a squared minus x squared. If you did the substitution x equals a tangent theta, so tangent theta is x over a, since that is opposite over adjacent, we get this right triangle, and you can figure out all the trig functions from that. And finally, if you let x equal a secant theta, so secant theta is x over a, so secant is the reciprocal of cosine. Cosine was adjacent over hypotenuse, so therefore secant is hypotenuse over adjacent, and we get this right triangle, and from that right triangle you can figure out all of the other trig functions. Now for the rest of this video, I'm going to show you how we can use this to find an integral such as the integral of the square root of 3 plus x squared over x. So first, you've got to look at what quadratic expression, what quadratic radical we have here. And in this table, we can see that we've got one of this middle form, which means we want to let x be a tangent theta. But this doesn't have a perfect square. This doesn't have a perfect square in it. It just has a 3, but that's no problem. It just means that a is the square root of 3. We always do the general case with a squareds, but if there is no perfect square, you can always let a just be the square root of the constant term inside the quadratic radical. So going from that table, or just from memory, we now get that x is radical 3 tangent theta, so dx is radical 3 secant squared theta d theta, and the square root of 3 plus x squared becomes the square root of 3 secant theta. Next, we need to plug all this into the integral. So the radical part here becomes the square root of 3 secant theta. The bottom, since x is square root of 3 tangent theta, the bottom is now the square root of 3 tangent theta. And the dx becomes square root of 3 secant squared theta d theta. This all simplifies down to the square root of 3 times the integral of secant cubed theta divided by tangent theta d theta. Now, often when doing these, I really don't know what to do at this point. So just to kind of clear the head a little bit, I just convert everything into sines and cosines. So since secant cubed is equal to 1 over cosine cubed, and tangent is equal to sine over cosine, and it's in the bottom, you get that one of the cosines cancels, and everything becomes the square root of 3 times the integral of 1 over cosine squared theta sine theta. This I rewrite as the square root of 3 times the integral of secant squared theta cosecant theta. Now let me just point out here that it took me a lot of tries to try this. I tried many other ways of doing this, by converting it under the other trig functions, by trying integration by parts, by trying substitution. However, it was only when I expressed this as the integral of secant squared theta times cosecant theta that I was able to get the right answer. So just because I come up with the right thing here, don't think it was easy. It took a lot of work. At any rate, in this form, we now use integration by parts. A bit of a typo here, but we let u equal cosecant theta, so dv is secant squared theta. And that means when you take the derivative of cosecant theta, we get that du is minus cosecant theta cotangent theta d theta. And since dv is secant squared theta, v equals tangent theta. That's why I liked choosing dv to be secant squared theta. So therefore, using the integration by parts formula, we get that our integral is equal to square root of 3 times our uv, which is cosecant theta tangent theta, minus the integral of v du. So minus the integral of tangent theta times minus cosecant theta cotangent theta d theta. This simplifies to square root of 3 times cosecant theta tangent theta plus the integral of cosecant theta. And cosecant theta, we know its integral because we knew the integral of secant theta. We just take the integral of secant theta, put a minus in front, and change every function to its corresponding cofunction. And therefore, we get the square root of 3 times the quantity of cosecant theta tangent theta minus natural log of the absolute value of cosecant theta plus cotangent theta plus c. At this point, I use the right triangle for x equals a tangent theta. Actually, x equals square root of 3 tangent theta. So that was this right triangle. And from this right triangle, we can read off all the trig functions and replace them. So for example, we want to replace cosecant theta. Well, cosecant theta is equal to the hypotenuse over the opposite. So it's going to be the square root of a squared plus x squared over x. So in this case, we get the square root of 3 plus x squared over x. Similarly, tangent is the opposite over adjacent, so it's just x over a in this case. So tangent is just x over the square root of 3. Cotangent, being 1 over tangent, will be the square root of 3 over x, and I plug it all in and get the final answer of the square root of 3 times the quantity of the square root of 3 plus x squared over x times x over the square root of 3 minus natural log of the absolute value of the square root of 3 plus x squared over x plus the square root of 3 over x. And please don't forget your plus c.